Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the types of electron emission and work function. So first of all, we know that when any free electron is ejected out of any metal surface, the metal surface acquires some positive charge on it, due to which that electron is being pulled back into the metal surface, and therefore uh, to escape that pull of positive charge on the surface, we need to give some energy to this electron to take out it from metal surface, and this minimum energy required is called as work function. So work function is the minimum energy required to eject a free electron from the metal surface. And for platinum, it is 5.65 eV, and for cesium, it is 2.41 eV. Okay, so these are the values of work function for these two metals. Now let us discuss about the methods that how we can eject the free electrons from the metals. So the first type of method is thermionic emission. So now thermionic emission is the type of emission in which we provide that minimum energy to the metal surface or to the electron by heating that metal surface. So by heating sufficiently at higher temperature, we provide that minimum energy to the free electrons and they are ejected out, and this type of electron emission is called as thermionic emission. Now, the second type of emission is the field emission. You can see that we know that if we apply 3 into 10 raised to power 6 volts of potential on air, then air, which is normally a non-conducting medium, becomes a conducting medium. And this phenomena is called as corona discharge. We have already discussed the corona discharge in electrostatics. So if we apply a sufficiently high electric field or magnetic field, and moreover electric field, because magnetic field could not apply any magnetic force on the charges which are at rest. So if we apply a strong enough electric field on the metal surface, then due to that pull of electric field, electrons are also ejected out, and this is called as the field emission. And the other type of emission is secondary emission. This is the third type of emission. So secondary emission is the emission in which we bombard fast moving electrons on any metal surface, and some of the electrons knock out the inner electrons of the metal, and this type of ejection is used in generating the X-rays. We will study the X-ray in detail in later on videos, and this is called as secondary emission. Okay, and the emission which we will be discussing in detail in this series is photoelectric emission. So photoelectric emission, as its name suggests, that photo means light and photoelectric emissions means that we emit the free electrons by incidenting sufficiently high enough sufficient energy light on the metal surfaces, and this effect is called as the photoelectric effect, and we would be discussing the photoelectric effect in detail. So now let's just move on the photoelectric effect and let us discuss the history of photoelectric effect. We know that Heinrich Hertz discovered the electromagnetic waves, and they propagated and produced the electromagnetic waves in the famous experiment which is called as Hertz experiment. And his assistants Lenard and Helmholtz observed that there was a zinc plate that was kept connected to the electrometer nearby, and that was becoming charged when electromagnetic waves are falling on that zinc plate, and they quietly observed this phenomena from 1886 to 1902, and they used the principles of classical physics, but obviously they were not able to explain this phenomenon on the basis of the theory of classical physics, because this phenomena is explained by the particle nature of the light. And later on, when Max Planck proposed the quanta theory, the particle theory of light, and then Albert Einstein uh, explained the photoelectric effect on the basis of the particle theory of light, and he was awarded with the Nobel Prize for this effect. Now, and obviously, the photoelectric effect was completely explained by Sir Albert Einstein, but in the history, the name of this, the discovery of the photoelectric effect is being registered on the name of Heinrich Hertz. Okay, that is the sad reality, but this is the reality. So now let us discuss the failures of the classical physics theory to explain the photoelectric effect. The first failure was the intensity problem. Now, according to the classical physics, the energy of the wave is its intensity. Obviously, we have studied the waves, and we assume that energy is obviously intensity. And hence, on increasing the intensity of a given radiation, the kinetic energy of the free electron should increase. But due to the increase in energy of the incident radiation on the surface, but practically it was observed that kinetic energy of the ejected electrons was independent of the intensity of the given radiation. So it was observed that if, let's suppose, we are incidenting ultraviolet radiation on any metal surface, and eventually we are increasing the intensity of that radiation, it was found that the electrons which were ejected from the metal surface were having the same kinetic energy. The kinetic energy of those electrons were not changing. So this was the practical observation, which was not matching with the theoretical explanation of the photoelectric effect according to the classical physics. Hence, this was the first failure of the classical physics to explain the photoelectric effect. Now, there was many failures, but we are pointing out just the three main failures. The second failure was the fact that according to the classical physics, when these radiations are incident on any metal surface, they are absorbed on the surface, and then free electrons of the surface are ejected out of this metal. And this complete process of incidence of the photons and ejection of the free electrons would take some time, and therefore, according to the classical physics, there should be a time lag or time delay between the incidence of the photons and ejection of the electrons. But practically, it was observed that there was no significant time lag or time delay between these two events, and again, this classical physics theory was not able to explain this practical observation. Now, the frequency problem was that according to classical physics, electrons must be ejected from the surface of the metal irrespective of the frequency of the radiation, provided that the sufficient amount of intensity of the radiation is incident on the surface. But practically, it was observed that the electrons which were ejected were not depending on the intensity of the radiation. In fact, they required a minimum amount of frequency of the radiation to get out of the metal surface. So again, according to classical physics, there should be a minimum amount of intensity of the radiation for electron ejection, but practically there was a minimum amount of frequency irrespective of the intensity of the radiation for electron ejection. And again, this was a big failure of the classical physics to explain the photoelectric effect. Now, this was the complete history and failure of classical physics to explain the photoelectric effect. And in the next video, I'll be discussing the laws of photoelectric effect given by the Albert Einstein and complete explanation of photoelectric effect. Thank you.